All right. Further application. It's a really cool application. I really like this application. You may like it too. All right. What is it called? Implicit differentiation. You just stick to this word implicit. It's not explicit, right? Then it's implicit, right? Okay. We start with this thing called the Cartesian equation. The key thing is that when you're looking at Cartesian equation, there are no functions. Cartesian equations are about Cartesian coordinates. What are the Cartesian coordinates? X and y, right? These are not function variable x and function y. These are just one point in xy coordinate plane. That's what that one's for. Like that, right? Make sense? 1 comma 2, 3 comma 5, those x and y, not function variable. That's Cartesian coordinates. Cartesian equation means that xy coordinates that satisfy this equation. So I'm looking at 1 comma 0 there. You know where 1 comma 0 is. I don't have to put x, y coordinate system there, right? Does this one satisfy this equation? Answer, yes or no. Here's how you do it. You plug in y value there, where every y value is replaced by what value here? 0, right? All the x value is replaced by 1. You plug in 1 there and see what you get. Okay, let's do that. What do you get in the left-hand side? 0. Sine of y, 0, 0. Y, 0 cubed is 0, right? 0 plus 0. What about right-hand side? X equals 1, correct? 6 minus 1, what is it? 5. So what's your conclusion? Is this x comma y satisfy this equation or not? No, it doesn't. Therefore, the graph associated with this Cartesian equation doesn't pass through that exaggerating. Pass through somewhere else. It doesn't pass through that point, right? What passes through is a collection of all points in here. They all satisfy this equation. If I put, this x coordinate and y coordinate there, if you plug it in there, left-hand side and right-hand side, perfectly equal. Collection of all those points. That's the graph of a Cartesian equation. That is a Cartesian equation. This is a Cartesian coordinates. What is this one called? Graph of Cartesian equation. Graph of Cartesian equations. Right? Ring a bell? Okay, there's no functions. Um, is there any way to sketch this one easily? And you can use Wolfram Alpha. All right? Most of the calculator, I don't think it does this one. Well, here it is. It's really neat. The command is contour plot. Contour plot, and then you write down the equation. Hope you see that equation typed in, right? Sine of y plus y cubed equals 6 minus x cubed, right? And then let it know the window size you want. I want to look at x from -3 to 3, y to -3. This is your choice, right? You have to just trial and error to pick out a nice region where this interesting thing is happening. If you look at region all the way over there, you're going to find this graph just looks like that. It's just boring graph. But if you find a good region, you see a lot of bending around it. So by playing with it a little bit, if you look at -3 to 3, -3 to 3, you have this nice graph. What is this graph about? This is a collection of all the points within -3 to 3 that satisfied all this equation. Where was 1 comma 0? 1 comma 0 is right there. No wonder it doesn't pass through, right? Okay. But there is some point pass through, and those are the points. If you plug it in there, it's satisfied. It shows you what those points are. Fair enough? Contour plot, and you can sketch the graph. By looking at this one, in pre-calculus, we apply something called the vertical line test. Do you know what that is? You draw a vertical line, right? And what is the conclusion out of that? If it defines a function or not. Very, very important key. So as you put vertical line here, how many intersection points do you expect? Always one, right? How about right here? Do you think that, it could be Is there something like that? If so subtle you don't see it, but you can have failed the vertical line test. But do you think that's happening around here? Doesn't appear so, right? So let's assume that it doesn't happen. So pass the vertical line test. And then we're saying it's a function, correct? That's the conclusion. It's a function. What does that mean? All that means in mathematics is a function is the following. Given an input, what would your estimate for x value here is? If I'm pointing somewhere here. Negative 1.2? No. Negative 0.6? Would that be fair? This is negative 1, right? Fair enough? That's your input value. What is your output value? What's your estimate? 1.7? Yeah. If your input is negative 0.6, your output value is what? 1.7. So would you believe that if you go through all this value, there's a corresponding output values there, right? So we see that input and output table with 1,000, hundred thousands of points in between there. We see that, right? But no one knows the formula. No one knows if I give you an arbitrary value, let's say 3.5, what algebraic procedure you go through, get this value 1.7. Is there an algebraic formula? The answer is no, not always. Like this one in here, there's no way you can isolate y and have everything on the right hand side x, right? That's what we're doing. Isolate it. It's not possible algebraically. Okay? It's not that human beings fail to do that. The mathematicians have a way of arguing that it is not possible to do so using sine and cosine and radical symbol and the notation we have. So functions out there, but we do not have sufficient notation to describe this function. Fair enough? But still mathematicians like to say function is defined. We just do not have a formula. Exact formula. Fair enough? All right, that's the situation. Miserable situation. But I'd like to, let you guys know these fancy theorems. We're not going to go into this theorem, but make this mathematics more logical. Here's how it goes. There are certain tests you go through to the Cartesian equation, and this theorem, something called implicit function theorem, tells you that function you see from computer graphic images is actually a well-defined function in calculus. What kind of function is it? Differentiable function. Even we don't have an even formula, right? But they're claiming that function actually has a derivative. So this fancy implicit function theorem tells you that there's a function out there. We cannot write it down exactly, but it's a differentiable function, right? That function is called f of x. We don't have a formula. We just have a name. In general, we don't have notation. It is implicitly defined. It means it's abstractly defined. We don't have a formula for that. Okay? So it seems like terrible situation. Why on earth is there a section about this one, right? If you can't compute exactly, what do you do? Thank you. Approximate it. We approximate it. If you can't calculate exactly, we're going to approximate it, right? Do you know how to approximate it? The only way we approximate in this course is linear quadratic approximation, right? To linear and quadratic approximation, what do you need? You need the value of a derivative at that point, right? And value of a second derivative. Okay? So in this section is all about there is a special point for which we can easily compute. Then derivative is easily computable. All right? In general, it's very difficult to compute. But there is this nice point I can easily compute by hand. Then you can compute the derivative by hand there as well. So that's what this focus is about. Then around that point, we use linear and quadratic approximation. All right? I hope the theme makes sense. So for now, we focus on computing the derivatives. Strange. We don't even have a formula, but we'll be computing derivatives. Actually, the values of the derivatives. Hope that makes sense. All right, here's an example. What is the title of this section? Implicit differentiation. You don't have explicit formula. We'll do that implicitly. All right. The situation is like this. What is the name of this equation? Cartesian equation, right? So that's how it started. That is a pre-calculus notion, Cartesian equation. Now we're going to pass something called the functional equation. He said that was a Cartesian equation. Now he called it something different, functional equation. And I said that when I was mentioning Cartesian equation, there is no function. It's just coordinate x, coordinate y, right? Now it becomes a functional equation. I have to bring in the function. That function is y equals f of x. How is f of x is defined? Abstractly defined. How is f of x? Implicitly defined. We don't have a formula. We only know the ghostly existence coming from implicit function theorem. Fair enough? All right. Now this one was a Cartesian equation. Now it changes in your mind like this. Sine y is replaced by that function f of x in there. Does that make sense? Now that y there is changing to function f of x with the third power, correct? Is equal to right hand side 6 minus this was a Cartesian equation raised to the third power. Now this is the cubic polynomial. Change to function. Now x is a variable. Right hand side is explicit function, correct? Left hand side is implicitly defined function because we do not have explicit formula of f of x. Now that was before Cartesian equation. Now this is a functional equation. If you have functional equation, according to the implicit function theorem, you can differentiate it. What is the derivative of this guy? 0 minus 3 times x squared, right? Feel free. Go ahead and try left hand side. Let's try it. What is the left hand side looks like, a derivative? I'm going to write d dx in between this arrow. What we did is differentiate with respect to x. Very important here, thinking about d dx. Now we're differentiating it with respect to x, right? What is it? Cosine, right? Cosine f of x. What rule am I using? Chain rule, right? Chain rule. What are you supposed to multiply? Derivative of f of x. So how about this one? Does that look all right? Yeah. Plus, how about this one? Like someone like to go for it? What rule comes to your mind? 3. What rule? What is the name of that rule? Generalized power rule, also chain rule. Both of them work, right? F of x raised to what power? Squared. Multiply by derivative of underneath the third power. This is best we can do, right? Yes. That's a generalized power. Remember, is when you do u to the third power d dx, right? That's what this one is, right? And then you have to enter du u to the third power du dx. That's the chain rule. So when you're differentiating, you get 3 times u squared, you're back to that, but there's out there du dx. That's a chain rule. When you're differentiating this one, treating this as one variable, you have to do a little bit more. That's what chain rule says. You have to multiply the derivative of f of x. Good? All right, that's it. That's the best you can do. Right-hand side is explicit function. Left-hand side is still have implicit things stuck to it, right? Okay, so this is first time explaining this one. Nobody does it like this. People do it like this. Look at it here. People look at here and understand y is a function of x and go like this. Oh, I'm going to do this. Cosine of y multiplied by y prime. All right? I'm doing the second one. 3 times y squared multiplied by y prime. Right-hand side, 0 minus 3x squared. I want you to look at these two things. This is more explained. Everything is like explained in the correct context. And here, it's just an abbreviation. Y, I didn't replace with f of x, but in my head, I know y is f of x, whatever it is. Here is f prime of x. I just wrote y prime. Does that make sense? Yeah. So people do this, but what they're really thinking, not telling you, is this, right? Make sense? Okay. So what does y prime mean? Derivative, right? But this is all about xy coordinate system, right? In xy coordinate system, the value of y prime means what? Slope of a tangent line, right? Y is the y coordinate, and x is the x coordinate. Now we enter the functional equation. Now you're coming back to the Cartesian equation, right? Starting with the Cartesian equation, enter the functional equation, coming back to the Cartesian equation. So what does this mean in the Cartesian equation? Y prime is slope, right? Y is the y coordinate. X is the x coordinate in the x plane. That transition makes sense? Starting from Cartesian equation, go to a functional equation, come back to the Cartesian equation. Good? But we did this to figure out what this y prime is, right? So they wanted to isolate this y prime. And it is possible. So do you see y prime in the left-hand side common? Can you factor that out, y prime? What is it left with? Cosine of y plus 3y squared, correct? Equals negative 3x squared. Right? By staring at this one, what do you want to do? Right, divided by everything by what's in the parentheses, right? So what is that? Y prime equals negative 3x squared cosine y plus 3y squared. That's a final answer. I want you to go ahead and circle this one. But I want you to go back to the original question. What was the original question? Find y prime. But how does the answer look like? It looks like y prime, right? But in the right-hand side, it is not just in terms of x. There is still y stuck to it, right? This is called implicit differentiation. You cannot go all the way down to the x, but you can still use a y coordinate to describe y prime. It's not too bad, right? Fair enough? All right. So let me go back to the picture and understand meaning of this one. All right. Let me go back to the picture. I'm going to grab that. Forgot to copy this one. Copy there. All right. Let's simplify. What do you think the coordinate there is? 1 comma. 1 comma 1.7. Was that fair enough? Is that fair enough? Yeah, 1 comma 1.7. All right. My question, calculus question, is that if I draw what kind of line? What kind of line am I about to sketch? Tangent line. Tangent line like that. Yeah. It's passed through right that point right there. And its coordinates 1 comma 7. There's this m. And that's our fundamental question in this course, right? Draw a tangent line. What is the slope? What's the idea? How can I calculate? It's m. You know what that m is? This is your x coordinate, right? This is your y coordinate. What do we do? Where do you go? Yeah, we go here. We go to that formula right there. Let's do it. What is it? Negative 3 times 1 squared, right? Cosine of 1.7 plus 3 times 1.7 squared. Can you go and calculate this one for me? 1 and 1 to put parentheses in the denominator. Let me have that number. If you get a positive number, you did something wrong. Because I'm clearly seeing that is a negative slope, right? Yeah. Numerator is negative 3, simply it's that. Denominator is cosine 1.7 radian, please, and 3 times 1.7 squared. Anyone else got a similar number? Maybe you forgot the parentheses. What is a new number? Yeah. All right, that looks about right if it is in the correct scale, right? I think it's in the correct scale. So that's roughly 0.3, negative 0.3 looks right. Make sense? All right. All right. Last question. Why did we calculate this? Why do we care about this derivative? Yeah, why do we find a slope? No, that was a vertical line test. Before I care about this derivative, and someone answered that there's no explicit formula, right? What do we want? Approximation, right? How do you approximate? Linear or quadratic approximation. What is needed to linear and quadratic approximation? F prime and F double prime, right? So this is how you calculate F prime right there. And this is a linear approximation, right? So what is a linear approximation? At linear approximation at where? What do you think is? C equals 1 x value, right? 1. What is it? 1.7. Do you see that? That's 1.7 there. And what is the slope? Negative, thank you. 0.3512 multiplied by x minus 1. That's the C value right there, right? That's this function Lx. And it's going to be pretty good approximation around that neighborhood, right? But not good enough, right? Yes. That's right. You have to make that preparation first. That requires a little bit of doodling and some calculation. Once you have that around it, we have this mechanical way of going about it by hand. So that's exactly correct point. You have to deal with that one point first, then rest of the part is a fairly efficient way of calculating. So how to improve this approximation? Quadratic approximation. You enter quadratic approximation. You got to calculate what? Y? Yeah, y double prime. You have to look at this expression in here and, just do it. And just go ahead and calculate second derivative one more time. Right? That's that's why the just do it is for. No, it's very reluctant to do it in the early morning, right? But for better